When you write a class like this, what do you think this object looks like in memory? Many people would say an int plus a char. But if I asked you, what is size of A, you might guess 5. If you really think that way and run it through a compiler, whether it's GCC, Clang, or the one we commonly use like VS on a 64-bit system, the result will definitely be 8. Why is that? Why are there an extra 3 bytes out of nowhere? This isn't a compiler error, nor is it memory waste. This is the core concept we need to understand first today: memory alignment and padding bytes. And this isn't just some random rule C++ made up. It's a hard requirement from the CPU. First, we need to understand, why do we need memory alignment? Many people think it's an unnecessary complication, but it's entirely for the CPU's operational efficiency. When the CPU reads data from memory, it doesn't read byte by byte slowly. It reads in fixed size chunks in bulk. The size of this chunk is the alignment unit. Moreover, modern CPUs only recognize aligned addresses. Unaligned addresses are read very slowly. For example, a 4-byte int type by default requires 4-byte alignment. This means the starting address of this int variable must be a multiple of 4, like 0, 4, 8, 12. If this int variable is misaligned and happens to straddle addresses 4 and 5, spanning 2 memory chunks, then the CPU cannot read it in one go. It must access memory twice, and after reading, it has to perform data splicing and bit shifting operations, causing efficiency to plummet. In extreme cases, some embedded CPUs might even trigger a hardware exception, causing the program to crash directly. So, to balance CPU performance and also adhere to the industry standard ABI specifications, which ensure that code compiled by different compilers can call and be compatible with each other, the compiler sets 2 rules. These 2 rules are the sole criteria for calculating the size of a class. The first rule is the member alignment rule. The starting memory address of each member variable must be an integer multiple of its own type size. This is called natural alignment. The second rule is the overall alignment rule. The total size of the entire class or struct must be an integer multiple of the alignment unit of the largest fundamental member within the class. If it's not enough, the compiler automatically inserts empty padding bytes to make up the integer multiple. These empty bytes are called padding. They hold no actual data. They are just placeholders. Back to the example at the beginning of the video. In a 64-bit system, the compiler defaults to 8-byte alignment. The first member of class A is an integer variable, x, occupying 4 bytes. Its starting address starts from 0. 0 is an integer multiple of 4, fully meeting the alignment requirement. It occupies memory addresses 0, 1, 2, and 3. The second member is a character variable c, occupying 1 byte. Its starting address follows x at address 4. A 1-byte variable has no address restrictions. It can be placed anywhere. It occupies address 4. Now let's calculate. We've used 5 bytes. But look at the overall alignment rule. The largest member in class A is int, with an alignment unit of 4 bytes. So the total size of the entire class must be a multiple of 4. 5 is not. The nearest multiple of 4 is 8. So the compiler automatically inserts 3 padding bytes right after char c, occupying addresses 5, 6, and 7. So the complete memory layout of class A would look like this. The total size is 8 bytes. Now you understand where those extra 3 bytes came from, right? It's not the compiler adding them randomly. The rules require that they must be added. Let's try a different arrangement. Many people think that just by reordering the members, you can reduce the memory size. Look at class B on the screen. What do you guess Sizeof B is? It's still 8 bytes. Why? Because int requires 4-byte alignment. Char c occupies address 0. To make the starting address of int x align to a multiple of 4, address 4, we must first insert 3 padding bytes after c, so the layout becomes like this. So when are padding bytes not needed? Look at class C again. All members are char type. The largest member is 1 byte. The total size is 4 bytes, which is exactly a multiple of 1. There's no padding, so size of C equals 4. Perfect. Here's a very useful piece of practical knowledge. Arranging member variables in descending order of type size and grouping members of the same size together can minimize padding bytes to the greatest extent. This saves memory and also improves CPU cache hit rates. This technique is especially useful when writing low-level code. Based on the previous content, can you figure out why this works? Now that we understand the basics of alignment and padding, let's look at one of the most core features of C++, virtual functions. Many people know that virtual functions enable polymorphism, but they don't realize that as soon as you add a virtual function, the object's memory layout changes entirely and its size also increases. Let's modify class A from earlier and add a virtual function. Now I ask you again, on a 64-bit system, what is size of A? The answer is 16 bytes, double the previous 8 bytes. The extra 8 bytes are the virtual function table pointer, or vptr, sneakily inserted by the compiler. Let me elaborate a bit. Virtual functions aren't some kind of black magic. The essence of polymorphism is a hidden pointer plus a function table. In simple terms, as long as a class has a virtual function, the compiler generates a global virtual function table, vtbl, for that class. All objects share this single table, which resides in the read-only data segment of the program. This table stores the memory addresses of all the virtual functions. And each object comes with a hidden vptr, usually placed at the very beginning of the object's memory layout. This pointer points to the virtual function table of its own class. In a 64-bit system, a pointer is fixed at 8 bytes. Adding the 4 bytes for int gives a total of 12 bytes. The largest alignment unit is the pointer's 8 bytes, so we need to add 4 more padding bytes to reach a multiple of 8, resulting in the final size of 16 bytes. When we usually use a base class pointer to point to a derived class object and call a virtual function to achieve polymorphism, the underlying mechanism is, first, get the object's vptr to find the virtual function table, then find the corresponding function address in the table and call it. This involves one extra pointer indirection. For example, this line of call, son is a derived class of a, overriding the virtual function f. When calling function f through the pointer p, the CPU first reads the vptr from the object's head that p points to. Finds son's virtual function table via the vptr. Finds the address of the overridden function f from the table. Finally calls the derived class's function, completing the dynamic binding. What about multiple inheritance and the diamond inheritance problem? Let's look at the simplest case first. Ordinary multiple inheritance with 2 independent base classes and a derived class inheriting from both. No virtual functions. The memory layout of the derived class C is very structured. It follows the inheritance order exactly. First, place the members of the first base class A, then the members of the second base class B, and finally the derived class's own members. Size of C equals 8 bytes, no padding. Very simple. But once both base classes have virtual functions, the situation gets complicated immediately. The object of derived class C will have 2 virtual function table pointers, vptr. One belongs to base class A, and the other belongs to base class B. In a 64-bit system, the layout would look like this. Size of C equals 32 bytes, several times larger. There's also a crucial detail here called pointer adjustment. When you write the line of code shown on the screen, this PTR pointer won't point to the start address of the object. Instead, it will automatically shift backward by 24 bytes to point directly to the location of the B subobject. This is done automatically by the compiler to allow the base class pointer to access its own members normally. This is a core underlying concept in multiple inheritance. Let's move on to the classic diamond inheritance problem. This involves a grandparent class, base, 2 parent classes, son1, son2, inheriting from the grandparent, and a grandchild class, grandson, inheriting from both parent classes. In this scenario, the grandson object would contain 2 copies of base S member X. Accessing X directly would cause a compilation error. This is the ambiguity problem. The solution is virtual inheritance, changing son1 and son2 to inherit as virtual public base. How does virtual inheritance solve the problem? The compiler introduces a new hidden pointer called virtual base table pointer, vbptr. Each class that uses virtual inheritance gets 1. This vbptr points to a virtual base table, vbtbl, which stores the offset needed to find the shared base members relative to the current object's start. In the end, the grandson object contains only 1 copy of base S members, typically placed at the end of the object. However, the cost is that to access a member from the virtual base class, you must first read the vbptr, look up the offset in the table, and then find the member. This adds an extra layer of indirection, making it slower. Therefore, virtual inheritance is a necessary evil to solve ambiguity. If you can avoid it, do so. Try to steer clear of diamond inheritance hierarchies in your projects. Through this video, you should have gained a general understanding of C++ object memory layouts. Alright, that's all for today's content. You can go ahead and run these examples in your own compiler, verify these Sizeof results, and see if they match exactly what we've discussed. See you in the next video.